Thank you. All right, everyone, welcome to Grand Rounds. I think we're having a little bit of good weather. It's hot, but it's not gross like it was over the weekend, right? We all agree? I looked up 2 days ago, because I'm on vacation, the cities with the best weather in the United States, and 18 out of the 20 are in California. None of them are in North Carolina. The two that weren't there, I think actually Greenville, South Carolina was there. Is that possibly got nice weather? I've never been there, but yeah, 18 of the 20 are in California. But for that, you pay 12%, state taxes. So you pay for that. All right, here's today's CME, Zoff map. But when it's really hot outside, I'd be willing to pay the 12%. So this week's All-Star nominated by Will himself, Tanya Schreiber, who is a communications person at Duke Neurobiology, who helped Will with the department's 2023 annual report. So Tanya, you have a coffee cup coming your way, and thank you. Upcoming events, the resident and fellows welcome is tomorrow, 6 o'clock at Duke Gardens. Suma told me that the residents and fellows can bring family, but faculty should come alone for size reasons. The vice chair and division director dinner is next Tuesday at Crowsdale. The end of year faculty meeting, to which the house staff is invited, and the fellows, if they want to come, is August 7th at 5:30. We have 2 locations reserved depending on how many people are coming. We'll make a big reveal that week. The theme is going to be the 10-year anniversary of the department, which happened on July 1. And then the Durham Bulls game is September 1, I believe at 6:30. Research roundup, Rick Bedlack was part of an article looking at how TDP43 and SOD1 proteins corresponded with the progression of ALS and neurobiology of disease. And Sneha Mantri was part of an analysis called Human in the Loop, which is, I think, you stick your head in a computer and you see, somehow people get involved in AI. I looked it up before I came over here, but understanding of subjective symptoms in Parkinson's disease. We'll get Sneha to do grand rounds this year and explain that to us. Katie Peters and Sveta, who's here. I saw Sveta come in, didn't I? There she, no, I was wrong. Okay, not Sveta. Looked at Behçet syndrome. Oh, look at the way I spelled that. Is there an apostrophe in Behçet's? I think there is. Someone with Behçet's who had central retinal artery and central retinal vein occlusion. Hai Chen Wang and Luke James were part of a paper in Neuron looking at the immunoregulatory protein PD-1 and its ligand and hippocampal function. That was a big deal. Sina Sasinajad is this week's Why Does He Love Neurology or Critical Care? And he talked about how teamwork and camaraderie, I really love that phrase, are really important in critical care neurology. Nicely said. I came across this. Does people know what cortex means in Latin? It means bark. Yeah. So it's the outside surface of something. In a tree, of course, the bark. I didn't know that. I thought it meant something much more glorious than bark. Today is Amazon Prime Day. Get in your orders. It's Etch-a-Sketch Day and National Eat Your Jell-O Day. Jell-O is the most widely consumed, disgusting thing, I think, in the world. Is there anyone here who likes Jell-O? Oh my God. You must have led a very deprived childhood. Couple of interesting on this day. So Sir William Osler was born on July 12, 1849. That's 174 years ago. He died at age 70. And 66 years ago was the release of the US Surgeon General's report linking cigarette smoking to lung cancer. I knew giving up cigarettes was a big deal when Dunkin' Donuts wouldn't let you smoke cigarettes in there anymore, right? That's when you knew they were, I mean, hospitals got rid of it. When Dunkin' Donuts got rid of it, you knew it was serious. Exactly. That's right, they had the ashtray right before you go in. All right, again, this is today's CME code. We're not going to have case presentations until beginning of August. So Today's Grand Round speaker, who is not being introduced by me, is Cameron McIntyre. So take it over. Let me S this out. We stopped it because Cameron's going to have to share.
Okay, so
yeah, yeah. I'll just stay up here and help him.
Sure.
Cameron, you go that way, and he'll come this way. Talk here. There we
We
go.
all have PhDs.
There you go.
Hi, everyone. It's my great pleasure to introduce today's speaker, Cameron McIntyre. Cameron did his undergrad and his PhD at Case Western. He was, for those of you who know Warren Grill, he was Warren's first PhD student. So I mentioned yesterday that he set the bar so high that he was instrumental in Cameron's future success. After his PhD, he did a postdoc at Hopkins and then another one at Emory. And then he went back to Cleveland Clinic before joining the faculty at Case Western. And then in 2021, it was our good fortune to be able to recruit him here. And since then, he's been a professor of biomedical engineering and neurosurgery. And he's really best known for some of the work he's going to talk to us about today, which is his work for deep brain stimulation, and particularly in modeling both the circuits and the effects of deep brain stimulation, primarily for movement disorders, but also for things like, for movement disorders, but also for things like mood disorders and epilepsy. He's also involved in a lot of different startup companies. He's done some really, really great work on augmented reality for neurosurgery, including for epilepsy and for DBS surgery. And he's really an expert on various aspects of stimulation and modeling. And so we're really thankful that he could come here and talk to us today. And please take it away. And thanks for coming.
Thanks a lot. Thanks for the opportunity. Really, happy to be here and excited to talk with you guys. And so, yeah, let's see. Okay, so it must be like, how do we, okay, there we go. So those are my conflicts. So today there are a couple people here that were, at the talk yesterday. So you're a real trooper. But this is going to be a completely different talk. So today I really want to talk more about deep brain stimulation, primarily for the treatment of Parkinson's disease, and the concepts of how, I would call it deep brain stimulation informatics will potentially play a role in sort of like transitioning this technology from something that's very much of a clinician hands-on based therapy into something that's, a parallel path between the clinician and some kind of computational clinical decision support system type intervention. And so deep brain stimulation, I'm sure everyone in this room already, knows about it, has seen it, has heard about it. The primary use cases are in Parkinson's disease and essential tremor, but then there's also, kind of smaller scale, uses in dystonia, epilepsy, obsessive compulsive disorder. And then there's, literally hundreds of ongoing exploratory, kind of trials with all kinds of other disorders, the two biggest being depression and Alzheimer's disease. And, there's no doubt, deep brain stimulation is an amazingly impressive clinical tool. We now have almost 35 years of experience with, kind of clinical application of these implantable deep brain stimulation systems, probably worldwide, especially if you count China. We're up to, over 200,000 patients that have been implanted with these systems. And, if you watch YouTube or if you actually interact with these patients, that like miracle outcomes are possible. The problem is that typical outcomes are really kind of mediocre. Now we've got a great, kind of movement disorders team here, and, with lots of experience and fellowship training and so I think we probably do better than average here. But when you look at the broad spectrum of deep brain stimulation across the country or across the world, you find that the, kind of the typical outcomes are less than you would hope for based off of, kind of typical screening criteria. So that leads to the question of, well, why are we having this range of outcomes in deep brain stimulation technology. It's very expensive. And so when you have that kind of expensive technology, the bar for expectation needs to be quite high as well. And so there's I would break it down into three different, kind of categories of issues that the field is currently dealing with and trying to understand how do we maximize benefit for every single patient, as opposed to having, whatever, 20, 30% of them be miracles and 20, 30% of them effectively be failures, right? So 20, 30% failure rate in a technology that has a total cost in the, $50,000 to $100,000 range is completely unacceptable, right? But that is the state of our field right now. So where are these, kind of issues of opportunity? So one is patient selection. So, the field of deep brain stimulation, you hear this tossed around all the time at DBS conferences that, well, only like 10 or 20% of the patients that could potentially benefit from the technology are actually getting the technology. And a lot of people blame the neurologist for that, frankly, if you aren't in that loop. And that's because they say that they're not referring to the neurosurgical services enough, right? That there are a lot more patients out there, but they're not getting referred. And why is that? Why is there that bottleneck there? Well, part of it, though, is that, it's not exactly clear what the appropriate patient selection criteria are that guarantee that someone will be a good responder or a good candidate for DBS. And so there are generic things that people have in mind about, kind of age, dopamine responsiveness. And then there's also a whole bunch of just dogma, that's very much center specific about what they think is the right thing and what they think is the wrong thing in terms of applying DBS in clinical care. Okay, so that's kind of one side of the equation. Another side is, maybe we're just not doing, maybe the neurosurgeons are really the failure point. Are they not doing a great job at, truly patient-specific customized surgical targeting? And are they, not even pointing at the right place, even if they do have good imaging data, right? So there's a neuroradiology side of this equation. There's a neurosurgical targeting side of the equation. And then there is the actual deployment of the electrode into that defined target, right? So there's all kinds of places where things can go wrong. And this is a super important issue because the electrodes are pretty small and the targets are pretty small. And if you're off by 2 millimeters, well, that can be the difference between success and failure of the device. But just our stereotactics, neurosurgical stereotactic frame systems, whether you're using frames or robots, doesn't matter. The mechanical accuracy of the system has a tolerance on its own of just 1 to maybe even 2 millimeters right there, right? So you have a situation where the need to get things into the right place is almost limited by the mechanical technology that we're using, right? Okay, so that's kind of that's another component of this. And then the neurosurgeons like to kick it back. And so I'm not a MD, right? So I am an engineer who has worked in deep brain stimulation for 20 some years. And I get to be a conscientious objector, outside observer that looks at the field and tries to help develop solutions. So that's why I can, play on both sides of the field. Okay, so the neurosurgeons like to kick back to the neurologists and say, well, the problem is not that I didn't get the electrode in the right place. The problem is that you can't program the device correctly. And so there are literally infinite stimulation parameter settings that can be selected with these devices. And at least in Parkinson's disease and movement disorders in general, we've got a pretty good idea of how to narrow that search space down to, whatever, maybe a couple hundred different settings that might be a good fit for a given patient. But still, that's 100 settings. There's no way that you can clinically evaluate each of those with any level of, detail. So you end up with always having this question in the back of your mind as the neurologist that, do I really have the right stimulation setting for this patient? And it's a totally dynamic thing because it's an interplay with the balance of the medications, right? So all these patients are still on medications. The whole point of deep brain stimulation really is to actually improve the on time of, of the medications, right? So it's really, the stimulation is an augmentation of the medications, but the art, and it's still very much an art of, DBS neurology programming, is finding that balance between the medications and having them work well with the stimulation. And that is a real challenge, and something that's done, really by personal experience more than at this point, kind of computational algorithm based things. But I've spent my whole career trying to develop computational algorithm type things that should, help make that process a little bit more standardized. Okay, so with that in mind, this talk is kind of geared towards, okay, well, let's try and think about how are we going to build a system that's going to provide that kind of computational clinical decision support, right? So as a data scientist, I don't really consider myself a data scientist, but let's just say that I was. If you looked at this field, you'd say, well, there's a whole bunch of different data types that we're kind of like thinking about. And right now, the movement disorder neurologists, they've already trained an artificial neural net in their brain that does all of this data integration, right? Some of them have a super awesome neural net. Some of them have a totally crappy neural net, right? The point of building a true clinical decision support system is that you build a neural net that's pretty darn good, might not be as good as the super world expert, but it's way better than the Joe Schmo, kind of not good person, right? And that you raise, the rising tide raises all boats. That's the underlying concept of these things. Okay, so what are the different pieces of data that we're talking about? Okay, so first we've got, kind of our anatomical type data. So you've got your patient specific MRI data sets. You've got things like brain atlases that, help you see things that you can't see on the MRI. Then you've got your electrophysiology type data sets. So intraoperative electrophysiological recordings of neural firing patterns, or now in modern times where the devices actually have continuous, kind of local field potential recording capabilities. You've got that kind of electrophysiology data. Then you've got your, kind of old school, behavioral outcome analysis measurements like UPDRS measurements, or some people even like to do, kind of quantitative kinematic stuff. Then you've got your medications, right? You've got a history of, kind of drug dosages and different drugs that patients have tried over time. And that's kind of like in the background of knowing what did or did not work for them. And then you've got their deep brain stimulation, kind of parameter settings. Okay, so these are all these kind of different types of data, but, in reality, they're kind of, geared towards two different sides of the equation. So one set of that data is really kind of geared towards the neurosurgeon. The other side of that data is kind of geared towards the neurologist. And frankly, I think we do a good job here at Duke of kind of having integration between those two worlds, but that's not universally true. And so what ends up happening is you've got, kind of from a data science perspective, you've got a little bit of a split of, all these different data sets, but in reality, they're all equally valuable to creating a, kind of functional outcome for that patient, right? So with this, kind of lead up, it doesn't take a rocket scientist to figure out, well, what would you do with that? Well, I'm going to put all that information into ChatGPT and it's going to spit out the answer for me, right? But unfortunately, or not surprisingly, that doesn't work, right? Why hasn't that worked yet? This is an obvious opportunity for kind of AI-based data integration. It's high profile, it's sexy, like we should have already been able to do this. Why haven't we done this, right? I could make millions of dollars if I could do this. So why haven't I done it? And the reason is it is way harder than it sounds, right? I'm so a good part of my life is spent doing, I would call it like medical software and device, kind of startup companies. And I'm so sick of computer science jackoffs and corporate wankers telling me how, AI is going to revolutionize healthcare. It's like they have no idea what they're talking about, right? So the reason is that it's very hard to think about how do you weight each of these different components when building one of these systems, right? There's thousands of components that go into each one of these individual pieces. And that's the thing. See, like an 8-year trained movement disorder neurologist, with fellowship training, they've been training that neural net for, whatever, 15 years or so, right? You can't just do it on the fly, without having a really well-crafted, goal-directed approach to kind of making that happen. Right. Okay. So I don't think that you're going to lose your jobs anytime soon. And I think that the whole point of these tools is actually not any way to replace that. They're just there to do this augmentation stuff, right? To give you guidance, especially in complex cases where you're kind of lost anyway, right? That's where I see the value proposition being. And we'll see if that's how it actually pans out. Okay, but what is the goal then? The real goal is, well, I'm going to have all of this kind of stuff on the left side. Is that the left side? I'm kind of bad with right and left, but anyway, on one side, you're going to have all this stuff that you're going to have preoperatively, right? And that is going to be stuff that you're going to want to feed into this, kind of predictor system. And what you're going to want to spit out is, number one, a patient-specific anatomical target point that will represent, the optimum placement for the deep brain stimulation electrode contact to modulate their specific symptoms based on their specific anatomy and their specific, kind of profile. And then you're going to want the system to also spit out, kind of at least a best guess at the, kind of initial stimulation trial that you're going to use for them. And then you're going to also want it to spit out, how should I adjust the medication dosages so that, all of this stuff works together, right? And so, there are many, many people around the world working on, kind of all these different pieces. We're not ready to try and put it all together into one giant soup and have it spit something out. Like, we're not there yet. But there are commercial systems now available that do, kind of part 1 and part 2. And those are, available from the major, kind of medical device companies. And we're just going to keep seeing more of this stuff. There's no doubt in my mind. However, there isn't yet a system that actually does anything with the drug dosages. And that's something that Kyle and I are actually, kind of working on right now that I think is really exciting. Okay. So as I talked about before, there's all these different pieces of this, but today we're just going to talk about one piece of it, which is just this kind of connectomics side of the thing. And I guess it's kind of related to, kind of the MRI based, components. But for now, let's, kind of like hone in on, what's going on in this one subcategory of these kinds of clinical decision support system development type activities. Okay, so the Human Connectome Project got started probably about, I don't know, maybe even 15 years ago. This was a major initiative led by the National Institutes of Health to use non-invasive, kind of human brain imaging technologies to try and develop large-scale connectivity maps of normal humans. And that was then, that project finished probably about 5 years ago or so, and established a baseline of data that has now been used in thousands and thousands and thousands of, kind of brain imaging type research studies. And with it has spawned offshoots of people doing effectively human connectome projects, but now specific in individual disease states, right? So if you've got these connectivity maps, tractography, resting state functional connectivity, whatever, you've got those in a normal subject population, then you collect that same kind of data in a Parkinson's patient population, then you can do these cross comparisons of, okay, well, what's fundamentally different? What can we use as, kind of biomarker identification differences or preoperative screening differences, right? These are things that, are really quite popular in that, let's call it the connectomic, evaluation literature right now. Okay, so that kind of stuff was the, sort of like the start point, and really got the field thinking about, well, how can we use these quote unquote connectomic data sets to start using them in combination with actual real patient, kind of analysis. I wouldn't call it patient care. We weren't there yet, but it's starting to get to that point where you would presumably use that kind of imaging data to actually customize things to individual patients. So I'm going to walk you through an example about how that might work in the context of, so this is a 7 Tesla MRI data set of a Parkinson's patient with subthalamic deep brain stimulation. This is a hand-based segmentation of the subthalamic nucleus in green. Obviously, this is the deep brain stimulation electrode its position's been estimated based off of a postoperative image. It's been co-registered to there. That red contact is the contact that's been used for therapeutic stimulation through that patient. And then we can, couple that kind of anatomical information with some, connectomic information. So in this case, we've got streamlined representations of the internal capsule as they flow through. This is a white matter superhighway that passes right by the subthalamic nucleus. So the subthalamic nucleus is the most common surgical target for treatment of Parkinson's disease with deep brain stimulation. But one of the things that you're always fighting with when you're doing subthalamic deep brain stimulation is you're trying to stimulate stuff that's inside that green area, but you're trying not to stimulate these giant white matter fibers that are right next door. I mean, they're just millimeters away. And so you're trying not to stimulate them. And that's usually the rate limiting step in terms of titrating the stimulation for an individual patient. So, but things like tractography, it's good at recreating the anatomical position and orientation of these giant white matter pathways. So it's something that's, kind of a fit of what the technology can provide us. So we can simulate then the, kind of electric field using computational models of the voltage distribution that gets generated from stimulating at this particular contact. And you can see, each of these different fibers that kind of experience a different influence from that electric field. And, we can kind of pull one of those fibers out and just look at it as kind of an individual. And we're going to then evaluate how the stimulation is going to, kind of impact that axon. So we can build what we call multi-compartment cable models of these individual, axons and represent their sodium, potassium channels. And that allows us then to evaluate the membrane response to the applied stimulation as, in terms of the generation of action potentials, which is really, that's our goal. That is the fundamental purpose of these stimulation therapies, is that we're trying to stimulate these axons to generate action potentials that then propagate, along the connections of that particular pathway. And what we're trying to do is we're trying to hijack those neurons. Those neurons, they're doing something wrong, or they're doing something that is pathological, or they're doing something that we don't want. And that is happening because they're firing action potentials in a certain pattern. And that is then resulting in some kind of neurotransmitter release somewhere that's causing some kind of problem, right? And the whole point of neuromodulation is I'm going to take whatever it is that you're doing, neuron, and I'm going to overwrite it. I'm going to impose my will as an electrode, and I'm going to make you fire the way I want you to fire. And once you're firing the way I want you to fire, you're going to stop doing whatever it was that you were doing that was bad, right? That's the 2-second answer of how the mechanisms of deep brain stimulation, right? Is we're taking these neurons and we're making them fire the way we want them to fire. Okay, so if we have a metric, then a modeling based metric of kind of predicting how an individual axon will fire in response to our stimulation, then, once again, doesn't take very deep thought to think, okay, well, now what I want to understand is how is a pathway going to respond? And I can look at that in the context of, as a function of my stimulation parameter settings, right? So you've got this stimulation, and you can translate that into some kind of pathway recruitment. So as those axons turn red, they're becoming under the control of the stimulation. And now we can say, whatever, 20% of this pathway is directly under our control now with the stimulation, right? And so you can link that then with this concept of, okay, we've got these connectomic maps that can be patient specific that are coming from our imaging data. Then we've got, kind of old school neuroscience based, kind of network block diagrams that tell us about how these different nuclei interact with each other. And that you can kind of put those things together and you start thinking about, okay, now here's what we're doing. We're doing network modulation with the stimulation. And in the context of, kind of subthalamic deep brain stimulation, we think that at least a good part of the problem about the, kind of network pathophysiology has to do with this little tiny microcircuit right here. So the STN is an inhibitory, excitatory, kind of connection with globus pallidus. And these guys, for whatever reasons that we don't really even understand, they get into a pathological beta band, kind of bursting oscillation. And the problem is that once these guys start spinning out of control, they start spinning everyone else out of control too, right? And the idea is that if we can stop this oscillation by stimulating here, or you can stimulate here too, or you can stimulate here, or you can stimulate here, it doesn't matter. It's a network phenomenon. And so if you stimulate in a node of that network and block the ability of that pathological oscillation to propagate, then you effectively can stop the symptoms of the disorder. And this is true in theory in epilepsy, although it hasn't worked as great as we'd hope. But it's also true in dystonia. It's also true in obsessive compulsive disorder. It's also true in all these other, kind of indications that people have been trying for DBS. Okay, but the problem, if we go back to that, is that, well, I showed you how we can kind of predict activation of the internal capsule, but, that's just one of like 20 different axonal pathways that are coursing through this subthalamic area. And most of these other axonal pathways, they're really quite small. They're small diameter fibers, they're small in size, they're crossing areas of giant anisotropy. And so that means that tractography is terrible, like really completely useless in my opinion. And so, so diffusion weighted imaging on a patient specific scale, it can't really tell us about all these other connections in this, kind of basal ganglia that we really care about. Like we really care about this pathway here called the lenticular fasciculus. And we really care about this pathway here, subthalamo-pallidal and pallido-subthalamic, but we can't reconstruct those pathways with, kind of typical clinical imaging type things. But we want to know how our stimulation is modulating those guys, right? Because we think those are the ones that we're actually targeting for therapeutic stimulation. Okay, so how do we get from these old school, kind of anatomist-based drawings that came from, kind of classic staining experiments to something that's actually a three-dimensional, model of axonal pathway collections that is something that could be used with modern brain atlas technologies and surgical planning and technology. Like this was kind of a hurdle for the field and still is. This is not an easy thing to do. Okay, so how do we make that jump? Well, one of my better ideas, I think, was, well, right at the time when, kind of holographic visualization headsets were kind of coming online, I got to, kind of use that technology before it was sort of publicly available. And one of the ideas that I had is, well, let's use this to actually take these old school neuroanatomists and let's integrate their skills with modern computational modeling and visualization, right? So we got, these famous basal ganglia neuroanatomists together, and Mikkel Peterson, the guy in the background there, he kind of built this anatomical framework so that we could have all this kind of 3D information and then have the neuroanatomists tell us, okay, we can build these models or these streamlines of all these different pathways, but we know they're not right? We know that they're in the right ballpark because it's based off of like some histological data that we've got, but we don't know, like the real trajectories. And that's what we need you guys for. So you guys come in, we're going to have these interactive sessions. You're going to tell us like, no, this is totally wrong, or yeah, this is good, but let's move it 1 millimeter, whatever. That was kind of how it worked. And so this idea that there's things that, you just can't do with modern imaging, clinical MRI type imaging, but there are these people that have that knowledge out there. You just got to figure out how to jam them together, right? So anyway, so these are videos of that kind of first, experience. And so this is kind of how that worked, where, we've got these histological data sets that tell us about where these axons are. We can overlay that with modern brain atlases. You can get kind of proxies of what you think the trajectories are going to be. Then you feed that into kind of like the preliminary model. Then you have the anatomists do this kind of like consensus-based definition. And then you spit out this, kind of, we call it a pathway atlas, right? So then you kind of, take the step of, how do you integrate that into deep brain stimulation analyses, right? So we have a, academic software tool, we call it StimVision, where you're kind of, trying to represent the stereotactic coordinate system that the neurosurgeons use, to do kind of, electrode visualization within the anatomy. So modern deep brain stimulation electrodes are kind of these directional electrodes here. So we're going to look at stimulation through this pink contact number 5. And what we want to understand is, before I showed you about stimulation of the internal capsule, but what we really want to understand is stimulation of all these other pathways, because they're the ones that we think are the actual therapeutic target of the stimulation, not the side effect generators of stimulation. So, here's this rat's nest of axonal trajectories coursing through there. We apply our stimulation amplitude and pulse width and stimulation parameter settings. That gives us an electric field that then will pull out the specific axons and connections that we think are directly activated in this particular patient for these particular stimulation parameter settings. And then you can try to correlate, those activation characteristics with some kind of a, behavioral outcome measure or electrophysiological, kind of evoke potential or something like that, right? So in this case, you can see, stimulation at the therapeutic contact, and that patient like stimulates lots of different things, like, and we don't know which of these are good, which of them are bad, which of them are, the most important. Like, that's the state of the field right now, is how do we tease this apart? So if you got 6 different pathways that are simultaneously being active, but only one of them is actually responsible for therapeutic benefit, well, like, that's a challenge. That's a data analysis challenge that the field is working very hard at right now. Okay, so, and then, the other side of this is back to, kind of how do we provide, guidance to the neurosurgeons? Well, you can put these deep brain stimulation electrodes in lots of different places, even within the same nucleus, right? So the subthalamic nucleus, I mean, it's pretty small. It's about the size of a Tic Tac. I mean, it's not a big thing, right? But there's many debates, especially in the neurosurgery community, that, well, some people are like, I want to stimulate in the central STN. And then other guys, no. I want to stimulate in the dorsal STN. No. I want to stimulate in the posterior STN. And there's good rationales of why these targets are quote unquote different from each other, but they're only like 2 millimeters apart from each other, right? And I already told you that the mechanical tolerances of the frames are only like 2 millimeters, right? So it's kind of like a big discussion of, noise. But what we can start to dissect is that even though these things are only 2 or 3 millimeters apart from each other, they actually do generate quite different pathway recruitment characteristics to them, right? So what we're looking at here is kind of the stimulus, we call these recruitment curves. So the stimulus amplitude on this side, and then the pathway, the percentage of the pathway that, would say is being recruited. And you can see that kind of the profile of activation. So different pathways get recruited at different levels and with different ratios, kind of based on being just a few millimeters apart from each other, right? And this is a good thing in some ways, because that gives us some hope that, well, maybe you could actually tease apart how tremor, the stimulation of the pathway for tremor might be different than the stimulation of the pathway for bradykinesia. And that could be a good thing, because if we knew that, then we could actually tailor the surgical placement of the electrodes and the stimulation parameter settings to customize it to treating specific symptoms, right? That's the vision of these kinds of tools. But we're not there yet. People are trying to get there. So how can we actually measure these things to start trying to dissect, whether or not we're stimulating the things that we want to stimulate, and being able to figure out which of these are the therapeutic settings and which are not. So one way you can do that is with intracranial electrophysiology. So this is some work from the UCSF group and Svetlana Miakinovic. And so, what they pioneered was this concept of, well, we're going to put a temporary subdural strip electrode over, kind of M1 and S1 in the operating room right after we, kind of put the permanent deep brain stimulation electrode in the STN. Then we're going to stimulate through the STN, and then we're going to record the cortical evoked potentials. And then we're going to try and dissect what do these little EPs translate to in terms of what we're stimulating down in the subthalamic nucleus. So the idea is that there's a major pathway coming from cortex directly into the STN. It's called the hyperdirect pathway. And there's also this pathway, the internal capsule fibers of passage, that we're trying not to stimulate. And people have hypothesized that this EP0 indicates activation of these internal capsule fibers of passage, very fast anadromic evoked potential that happens in cortex about 1.5 milliseconds after a stimulation pulse. And then there's a second peak, though, that happens about 3 to 5 milliseconds after the stimulation pulse. And they think that that is activation of this hyperdirect pathway, which I think is a therapeutic target, right? So you've got an EP that's indication of a therapeutic target, and an EP that's indication of a side effect, and that you could kind of pair those apart from each other. Okay, so can we actually line that up with biophysics? Because if you could, then that makes that argument even more interesting and stronger. So we can build these kinds of patient-specific connectomic stimulation models for stimulating the internal capsule fibers of passage. And you can do that same thing for stimulating these hyperdirect, kind of projections. And then you line up, kind of the act potentials that you would get out of those guys, and how long it would take for them to propagate from being stimulated here and then to go all the way back up to cortex. And you can line that up then with these, kind of measured evoked potentials that you see, in the experiment. And so, we're starting to get to the point where it's like, this is kind of like model validation, but it's also kind of like connectomic mapping of, kind of these circuits in the brain, right? The very initial early steps of doing that kind of thing. And, as time's gone on, these kind of correlation opportunities get more and more and more elaborate, right? So in the experiments, they stimulate with many, many different stimulation parameter settings, because each one of these settings really generates a different kind of evoked potential. And there's a real interest in trying to understand how those, kind of stimulation parameter adjustments translate into differences in both, evoked potential activity, but also, we can correlate these different stimulation parameters with different clinical outcomes, right? Functional outcomes. And you can see that as we've, kind of evolved with building these kinds of models, we can really do a quite amazing job of correlating kind of activation of, the pathways with activation of, or the size of these EPs. So that's giving us confidence that we're going in the right direction in terms of making these models able to make patient-specific level predictions of activation. And you can see that, we do pretty good job, right? We're talking about, kind of 0.6-ish, 0.7 type correlation coefficients. But the problem is that that's when you're thinking about things on a patient-specific level. If you try to take all the patients and jam them together into one big group and say, well, everyone's brain's the same, then everything falls apart and your correlations drop into kind of like the 0.3, 0.4 range. And that is also consistent with, these, alternative modeling teams out there that have been using what we call a group connectome approach, right? They don't do anything with patient-specific imaging. It's all within a giant atlas data set, and they try and kind of build these correlations about what parts of the brain are stimulated to create what kind of behavior. And once again, those end up with really quite weak correlation coefficients. So the field is kind of, now trying to figure out the methodology of, if everyone agrees that they think it's a good idea, that let's try and parse these connections in the brain with some kind of behavioral or electrophysiological measurements, because that sounds like a useful adjunct of knowledge and information, but we're not ready to really figure out the right details of exactly what's the right methodology to make that happen. But we can start building hypotheses around, which of these pathways we think are related to which symptoms. And, this is just sort of a guesstimate of that. Okay, so with the last couple of minutes, I want to, kind of show you some of the stuff that's like happening. That's like 10 years ago, I would have said, you're absolutely crazy. There's no way anyone would do this. But now they're doing it. So, and this is really because the worlds of epilepsy and stereo EEG have been blending with the worlds of traditional deep brain stimulation in a way that is really quite exciting and has been driven by, in many ways, kind of the NIH Brain Initiative, where there's, great interest in mapping, these kind of human brain networks using intracranial electrophysiology, and then using that to develop new therapies, right? So this is an exploratory clinical trial of deep brain stimulation for depression that's being led by Samir Seth at Baylor. And the concept here is that they're gonna, or what they have been doing is implanting permanent deep brain stimulation electrodes in ventral capsule and subcolossal cingulate, targets that have been known and demonstrated to produce therapeutic effect for deep brain stimulation of neuropsychiatric disorders. So they're going to put in these permanent deep brain stimulation leads, but in parallel, for 10 to 15 days, these patients have agreed to undergo temporary stereo EEG placement throughout the kind of prefrontal cortices to do these kind of EMU-based electrophysiological mapping studies of these, circuits that we really know almost nothing about in terms of, kind of these neuropsychiatric, kind of dysfunctional circuits. So really heroic experiments and really heroic patients really for being willing to do that. And at the time when Samir, this is Samir in the blue blazer there, at the time that he was planning this trial, I was just getting to the point where I was showing my kind of like neurosurgery friends what these prototypes of the holographic visualization systems look like. And, it was pretty obvious to all of us that stereo EEG, that this was the killer app for these kinds of visualization tools, because, that's a situation where you've got one, there's a growing appreciation for wanting to have all this connectomic information together. So very high density three-dimensional data sets coupled with 10 to 15, 20 trajectories, three-dimensional trajectories that are, they can run into each other. And are you sampling the right areas? Are you maximizing the amount of coverage for each trajectory? I mean, it's just the most complicated three-dimensional visualization problem I've ever seen. And this is the only tool that I've ever seen that actually allows you to integrate all that information together in a way that your brain can process it. So, so this was the very first time, I gave the thing to Samir and he's like, just get out of my way. I know what I'm doing, like, this is awesome. So we started then, kind of using this tool in this, unique clinical trial basically as a beta test of the technology. And it was, amazing, whether or not it has any impact on outcomes is like, that's a whole different kind of animal, but there's absolutely no doubt that it has an outcome, at least in our understanding of, we've got a hypothesis of where you want to put these probes, but now let's actually have some real data guiding that on a patient specific level. And that then allows us to go from some kind of an academic, kind of research plan based off of kind of the latest, greatest brain imaging data sets to then porting that into, your standard FDA approved, neurosurgical planning environment, to then being able to deploy that scientific plan, as accurately as possible through the robot, right? And so, this was super fun. I mean, this was the most fun, kind of engineering project I've ever worked on. And, this is, like days before the world shut down, like we did this first implant and this was like super fun to me. I mean, this was, like I said, it was a highlight of my research career. And I think that now there's many of these projects out. And so that was, 3 years ago. Now there's, probably across the country. I mean, most of them are, sprinkled at, the big name places, but there's probably, 10 to 12 NIH funded brain initiative studies that are, kind of doing these, stereo EEG based brain network mapping type studies of, patients that are not epilepsy patients, right? That this all came from epilepsy, but now it's growing a whole new, growing new arms to it. And the value of that is that it's allowing people to do these, never before thought of type stimulation mapping experiments where, you've got your deep brain stimulation electrodes distributed throughout the brain, but for each one of those DBS pulses, you can measure 256, 300 different evoked potential signals distributed throughout the brain simultaneously, right? I mean, like, it's just not something that we've ever been able to do before outside of the epilepsy EMU. And you guys, the epilepsy people, are used to doing that, but the whole rest of the world, they all thought you were crazy, right? Now they think you're the smartest people that ever were, right? So it's funny how these things kind of come and go. Anyway, as you might remember, the world blew up in 2020 and we couldn't do that like in-person stuff anymore. So we had to figure out how to make these holographic environments work with, kind of the new reality of like people weren't allowed to be in the same room with each other. So thankfully, Microsoft kind of helped us do that. And nowadays we never travel. Like nowadays we build the patient model, we load it on the headset, we FedEx it to the guy's offices. And then this is what, our planning meetings look like now. And Angela and I do these planning meetings now all the time. And so, and this is kind of what it looks like, right? So this is my office in Hudson. And then this is Nader Paradian's office at UT Southwestern. And this is Samir's living room. And, and this is just how we do surgical planning for these clinical trials now. And it's super fun. It's really interesting. And it's, I think a way easier to schedule these meetings too. Like, you don't have people flying around and anyway. And so, the technology keeps evolving and it's going to keep evolving, right? I mean, these things are going to just keep getting cooler and cooler and cooler. But, here's Samir's avatar hand in Houston moving this electrode in my office in Durham as, he's placing this electrode using connectomic, patient-specific connectomic models of the different pathways that we're trying to target to treat specific symptoms, right? I mean, I can't believe we're doing this. Like, I really can't believe we're doing this, but we are. So, in conclusion, I think, there's all kinds of new opportunities to build these computational modeling based clinical decision support systems. It's going to keep happening. The data keeps getting better, and eventually this will be common practice, right? And I don't know if that's going to be 5 years from now or if it's going to be 10 years from now. Like that, I can't predict. But I can tell you for sure that it's going to happen. So, all right, thank you. Any questions? Yeah, back there.
So given the new modeling, like the tracks, if you were to step back and look at the additional algorithms used for treatment tracks, planning and placement of TVS, was any of the present model that's used for the Connectomics predict that those were maybe somewhat deficient or not fully captured, specific regions, pathway or nucleus or optimal DPS?
Yeah,
Just
so
repeat
good question.
that.
So
Repeat it.
yeah. So the question was, well, were surgical planning strategies from 10 years ago, in some ways, now do we think of them as deficient or inaccurate or inadequate? And I would say that the answer is no. Like, I don't think that any of this connectomics stuff has changed. Maybe there's like a handful of neurosurgeons out there that are like, big early adopters, and they're like, oh, it's changed my practice. But the vast majority, let's say, 90% of them would be like, no, this is cool. I like it. It's informative, but it doesn't change the way I do things. Because the data is not mature enough to justify that yet either, right? They're a very cautious group, or at least in my experience, I find them to be quite a cautious group in that, they are willing to change and adapt, but only after we've got a mountain of evidence that says that the old way you did it 10 years ago needs to be replaced with the way that we do it now. And instead, what they look at as valuable with this information is that I want to see, whoa, that is a giant spider. I know, man. So what they want to see is, I want to do it my old way, and then I want to see what this new data overlays about the old way I did it. And I'm going to keep doing it my old way until there's enough evidence that says that, I really do need to move by 2 millimeters, because the new data says that I should be 2 millimeters over, but I don't trust it yet, kind of. Does that answer your question? Yeah. So I'd say that's where we're in that transitional phase. Yeah.
Jim?
I have a comment and a question, first of all. I find this all very interesting. The comment is, and T mentioned this yesterday, that it seems to me that movement disorders, and Parkinson's in particular, is low-hanging fruit relative to epilepsy, insofar as it's a persistent deficit as opposed to intermittent.
Yes.
And secondly, there's huge heterogeneity in epilepsy in terms of the functional neuroanatomy. So that's just a comment. My question is, I just wonder if you've exploited, or the field has exploited, animal models. I mean, you show beautifully all of these different variables, fields, the distribution of that current, etc. Might you sort that out in a well-circumscribed, well-defined, homogeneous animal model? Sort those out and then use that as the foundation for going and pursuing this in the heterogeneity of the human.
Yeah, absolutely. So the question was, I showed all this stuff about testing all these different things in the kind of human environment, but shouldn't there be a parallel path of doing all of that in a much more constrained and much more detailed scientific animal model type analysis? And the answer is yes. So it's just not my world. I used to, kind of try and do parallel monkey neurophysiology modeling with human, kind of modeling. And it just became, well, there's two factors. I'll just be honest with you. One is no one gave a damn about the monkey work we were doing, and it was taking forever, and it was super hard, and it was hard to fund. Whereas the human stuff, people loved it. It was easy to fund, and it was much higher impact. So that was the end of that, right? That doesn't mean that I don't think that there's value in, like, we were learning more doing those monkey experiments and doing that monkey modeling than we were with the human. But like I said, the world just wasn't appreciating it. And I think that's true with the rat side of things too. It's hard to think about, and this is another reason why I decided to make this transition of focusing almost exclusively on human, was especially, this is, I think, unique to neurostimulation in, comparing the effects of neurostimulation in animals and trying to make the jump of doing that same comparative analysis with microelectrodes in animals to macroelectrodes in humans. There are just fundamental physics things that make that very, very hard to do. The electric fields are different, the neurons, like the sizes, all those differences, they really make a difficult transition of trying to take data from the animal and put it into the context of the human. And so that was another factor that was kind of the nail in the coffin for animals for me. It was just too hard to make that jump. But there's many people doing it, and there's value coming from that. And I take value from it all the time, right? It's just, it's not our explicit focus. Does that make sense? Yeah.
Take one last one, Joe.
So given Jim's question about epilepsy, in the patients with refractory epilepsy, where you can put depth electrodes in and try and see where things are starting, where things are spreading, might you be able to come up with a patient-specific program of stimulation based on the pattern of what their spread is, based on the electrodes that get placed in that individual patient?
Exactly. So that's exactly the point of these, like I said, 5 to 10 brain initiative kind of exploratory clinical trials. They're doing this in epilepsy too, but also in these other indications. The whole justification for doing these stereo EEG implants is that they're building a forward model of stimulation-based neurophysiological mapping. Then they're feeding that into some black box AI system that's spitting out what the quote unquote, optimum stimulation should be to modulate the network. And that is then the truly, patient specific custom stimulation that is maximally interacting with the network. Now, my personal opinion is, that's a joke. Like, we're nowhere near doing that. But that is what the Science and Nature publications are all about right now. So yeah, you're right on target there.
All right, thank you, Cameron.
I don't know, but I'm not, that's someone else's problem. I can't sure that someone else has to.